But my rule of thumb is don't do it the day I give you the test back. Go home and look at it. And in fact, I even prefer if you write a comment and hand it back to me and I can look at it again if you don't like what I've done. And we're doing recursion. And then after today, you have a reading week, and I hope everybody, it's kind of a silly reading week in my personal opinion, because the purpose of reading week should be either you relax because you've gotten so stressed, or you get to catch up in your work, and we haven't done that much yet. It's pretty.
It's only been 4 weeks of school.
It's too early.
Yeah, it's way too early. It's really silly.
Are we going to have the test without coming Monday?
No,
So I went to Waterloo, and there they called reading week suicide prevention week, and the rule was you weren't allowed to do any work whatsoever. And so when I lay out the schedule, I always assume that reading week doesn't exist. So it's every other week, skipping reading week, right? So the test is not the day you come back, right? That's the day.
The day we start again.
The day we start again, and then it's the next Monday will be recursion, and as you've seen, what I really want in the recursion test is for you to convince me that you understand recursion from the perspective that I understand recursion, right? So, for example, if you were to say the algorithm calls this, which calls this, which calls this, then you will get a 0, right? What you're supposed to do is you're supposed to say, in this case you can actually kind of give code, right? Because you're given this instance. What do you do with this instance? You, if it's sufficiently small, you solve it yourself. Otherwise, you break it into smaller. You construct smaller instances which meet the precondition and which are smaller according to some measure. He gives you, your friend gives you the answer. From your answer, you get your answer, right? So those are the kind of things I want to see in the test. And also recurrence relations, right? There's going to be a recurrence algorithm, and you're going to need to know the running time of it. And so you'll have to be able to write down the recurrence relation and solve the recurrence relation, right? And how do you do that? Well, chances are you'll have A friends, and each friend is given an input of size n over b, and so you compute log A over log b, and you compare that to C, where the amount of work I personally do is into the C. Everybody kind of with me here? That's what you'll need to know for the test. All right, so let's talk now about something that can make. Oh, why does it always do this to me? Is there some secret to telling it really that I don't like it? Oh, here we go. So one thing that makes the problem a little harder is that, oh, that's not the one we want, is that sometimes I'll tell you, okay, that the input is this and the output is this, but that's not enough information for your friend for you to solve it recursively. You have to either give your friend more information, or you have to get more information back from your friend. All right, and this, what we're going to hear is just a little silly example of how to solve this problem in 3 different ways. And the first way we're looking at it is kind of, this is the obvious algorithm, right? The obvious algorithm. Remember, what we're trying to do here is you're given a binary tree, and you want to know whether it's a binary search tree. And what's a binary search tree is that for every node, everybody in its left subtree is smaller or equal to everybody in its right subtree is bigger or equal to it, right? So you can see that it's a binary search tree if the left subtree is a binary search tree, and the right subtree is a binary search tree. And the maximum in the left is smaller or equal to the root, which is smaller or equal to the minimum in the right. Right? Are we going to buy that? That tells you that it's a binary search tree. And the problem with it, as we talked about last class, is how many friends are there here. And this would be a fine question to put on a midterm, is saying how many friends are there here? And people should say there are 2 friends. Because what you do to a friend is you're giving them an instance that's smaller and meets the precondition. Right? So now, and solves the same problem, right? Same postcondition, right? So here, there's only 2 places where you're recursing. These guys are given instances that are smaller and meet the precondition, but it's a different problem, right? So they're not your friend. I mean, they're your acquaintance. Thank you. They're your helpers. Exactly. And so if we look at the running time, then I have 2 friends, each given assuming that the tree was balanced, then I have 2 friends, each with an input of size n over 2. But how much work do I personally do? What we would like to say is I do constant work, right? But am I doing constant work here? No, because my acquaintance, whoever said that, is doing the max and the min. And I have to count that as my work. Right? So if you look at this, you should just recognize this as being merge sort. Right? So you should know that it's in log n. I mean, maybe everybody doesn't say, hey, that looks like merge sort to me. It doesn't say merge sort to you. I have 2 friends, each given input of half the size, and I do in work to merge them. I mean, that's merge sort. But what happens if the tree is unbalanced? Right? Then one child doesn't do any work at all, right? Because there's nothing there. And all the work is on the other child. And I'm still doing work in. And now if you unwind this, I do work in, my friend does work n minus 1, and then his friend n minus 2, n minus 3, right? And that comes out to n squared. Right? So that's just an example of how you don't want to be redoing work. Right? So now we're going to look at 2 ways in which we can solve this problem easier. The one is we can get extra information from our friend. Right? Your friends can be useful people. You can make your acquaintances into your friends, or you can merge them somehow. What you do is you change either the pre or the post condition. Right? So here we're going to ask our friend not only to tell us whether the left subtree is the minimum left, is a binary search tree. We're also going to ask the friend what is the minimum and what is the maximum. Right? And now you're allowed to ask your friend whatever you want. You can ask your friend to give you the world if you want. Right? But if you do that, then you have to change the post condition, so your friend is meeting the post condition. And if you change the post condition, then what happens? It's a different problem, and you have to now do it yourself. Right? Anything you expect your friend to do, you have to do as well. All right? So we change the problem, so you give it a binary search tree, it tells you whether or not it's a binary search tree. You give it a binary tree, it tells you whether it's a binary search tree. It gives you the minimum value and the maximum value, right? And so if the tree is empty, then yes, it's a binary search tree. The minimum is positive infinity, right? The maximum is minus infinity. Remember that little trick? And then our one friend is given the left subtree and the right subtree, and they give us the answer, right? And you can have meaningful names here, right? Left is a binary search tree or not. Left min, left max. Right is right min, right max, right? Fairly reasonable names. And then your friend gives you those, and now you have to know, is it a binary search tree? What is the min and what is the max, right? So what's the min? It's the min of the left, the right, and the root. Right? What's the max? It's the max of the left, right, and the root. Is it a binary search tree? Well, if the left is, the right is, and now we have the left and the right. And we have the min and the max of right? And so we can do that same trick as we did before, and we can say yes or no, and we can answer the question. All right, everybody kind of got that? Now here's a...
Can you just show the positive and negative thing really quickly?
Why we do that?
Yeah.
All right, sure. So suppose that we have a list so far, and the maximum so far is a 2, and we read a 7, right? Then what's the code? Is the maximum up to here is going to be the maximum of the maximum so far and the 7, right? Does that make sense?
Yeah.
So we place, right, we go up to here and we place this with the 7. Now what happens if we haven't read anything so far, and the very first thing we read is a 7? When we get here, what do we want the maximum to be? Well, we've already read a 7. We want the maximum to be 7. So what do we want this to be? Call this question mark. We want the maximum of question mark in 7 to be 7. Right? Does that make sense? Right? What is the maximum of the empty set? You know, it's kind of meaningless. But what answer do we want to get from this question? We want to get 7. So what do you plug in here? Negative infinity. Right? Does that make sense? Now here's kind of a trick question for you. I ask, you know, here the left subtree we need the max, right? In the right subtree we need the min. Why do I ask the left subtree to give me the min?
You mean the max?
Right. I definitely need the max of the left. But if you'll note, the left guy also gives me the min. Right? So it seems like I'm doing extra work.
Because it's the same problem, so if we're asking for the right min, it needs to calculate it, so left min also has to be calculated.
Right. So for me to repeat that, a couple of answers. One is that the guy who's given this thing doesn't know if he's the left or the right. Right? You need one precondition and one postcondition, and the guy who's given the tree doesn't know if he's the left and the right, so he's going to compute, you know, both of them. Now, I suppose you could pass in here, are you the left or the right? Right? And then this guy would know whether he needs to compute the min or the max. But it's a little scary, right? Because suppose that this is the, you know, suppose you're sitting, this is your tree, right? Well, now this guy, he needs to give you the min because he's the right? But now this guy has to give you the max, but this guy didn't give you the max. You know what I'm saying? So it gets a little bit more confusing. So it's easier just to say, you know, it's not that much extra work to compute both of them. Right? So I don't know if we have a running time here.
Sorry.
Yeah.
Can you go back one?
Yeah.
When you say min equals to the min left, min right, and why do you do that? Why, you know that the right is the minimum is going to be, it's not going to be less, right? So why do we need to have that?
Well, I don't actually know that it's a binary search tree. All right, it becomes sort of a circular argument, right? I mean, maybe the reason it's not a binary search tree is because that's wrong, right? Good question, though. All right, so this is the running time we had before. What changes now in our running time? How many friends do we have now?
2.
What's the size of their inputs?
1/2.
And how much work do I do now?
1.
Right? I now do constant amount of work. Right? Everybody can see that if you go back to the code here. You know, this is just a constant amount of work. Right? I don't have any associates. All right, so here's another solution, and this is the one I really put in simply for amusement. All right, this one is saying, okay, I'm not going to change the post condition. I'm not going to change what information is sent back. What's going to be sent back is still a yes or no. But I'm going to give my friend more information. Right? I'm going to give my friend a binary tree, and I'm going to give my friend some value min and some value max. Right? And we need a well-defined problem here. And the problem is, they say yes or no to whether or not is the binary search tree, is it a binary search tree? And moreover, do all the values in the tree lay within the range between min and max? Right? That's when they'll say yes or no. Can I get the question? So I'm giving this extra information. Right? So I want to know all right, so one thing we need to know is whether the root, for it to be true, for us to answer yes, what do you need? You need that the root's within the correct range, right? And you need that the left subtree is between the min and the root, right? And you need that the right subtree is between the root and the max. Right? Does that make sense? So then that, oops. Let's go backwards. Then what's the algorithm? The algorithm, if it's an empty tree, then we say yes. And if it's otherwise, we check, is the root within the range min and max? And we ask our left friend, is the left subtree a binary search tree within the range min and the root? And is the right subtree, is it a binary search tree between root and max? And if all those things are true, we say yes, otherwise we say no. Does that kind of make sense?
We haven't told them what the initial min and max is.
Good question. Where did the min and the max come from?
First call. You'll give it.
Right. Good. So when we first call it, suppose I'm given a tree and I want to know whether it's a binary search tree. How do I call this routine?
Tree.
And then min and max.
Then min and max.
What values do I give?
Yeah.
Negative and positive infinity, right? That's how I solve it. That's how the first guy sets min and max, right? But then, look at min and max changes, right? Because the first guy might be given negative infinity, infinity, but then it's given, this guy is given negative infinity and the root, right? And this guy is given the root and positive infinity. And then his friend, right, he's given negative infinity and 10, right? Well, then he gives him some other number in the 10, right? So it sets as you go down. But we don't need to be tracing it down. What you're assuming is the problem is part of the precondition is you're given a tree and a value min and a value max, right? That's where those numbers come from, and you need to be able to solve this problem no matter what values are given here. Right? People kind of follow this example. Now, one thing, let me tell you, I would say about the half of the time that I give a recursive problem, you have to change the pre and post condition, right? But only do it if you really have a good intuition that you need to, right? And if you do it, if you change it, what are the things that you have to do? Or else I will be very mad at you.
Make sure that the friends are also inputting outputting the right things.
Yes. Yeah.
Write down what you've changed it to.
Yeah. Yeah, those are good things. Anything else? Yeah, so it's saying, tell me what the pre and post conditions are, right? Document that you've changed it. When you call your friend, now make sure it meets the new precondition. And when your friend returns, make sure that he returns things according to the new post condition. and make sure that you're given something according to the new precondition, and make sure that you solve that problem producing something according to the new postcondition. Right? Don't give me some weird mix and match thing stuck here and there, because then I get really upset. And you don't want me upset.
What do you mean that we have to change? Are you going to give us a fake one or a wrong one? Or is it going to work but it's different? What do you mean by that?
Well, this was an example as I say, write me a program that finds whether it's the minimum, whether it's a binary search tree. And then you say, oh, but I need to know the min and the max. Why don't I ask my friend for the min and the max? So you say, hey, I'm changing the post condition, so I also answer the min and the max. Right? All right, so let's go through these. These were slides, as I say, after I have a bad day of marking, I make slides. Right? All right, so, trust your friend to solve the sub-instances. Sub-instances must be smaller and must be instances of the same problem. You combine your solution given by your friend to create a solution for your own instance. Focus on one step. Do not talk about friends, friends, friends. Don't trace this thing out. You worry only about yourself. Don't micromanage. Solve instances that, if they're small enough, solve them on your own. All right, so let's come up with, so here's when I say half the class fails, this is the kind of thing that they give me. All right? And, the mark I want to give on this is -100. All right? If somebody puts a blank page, it's quite serious. If you put a blank page, I might just give you a 20, right? Because at least you knew that you didn't know, right? But if you give me shit like this, not only do you not know, but you don't know you know, and you don't know that you don't know that you don't know. You're just so lost. All right? So let's see what I hate about this. All right? Maybe you can even see some things here on your own, things that you hate. First we have the pre and the post condition, right? All right, so what do we got? Tree is a binary search tree, and k is a number bigger than 0. That's reasonable. And outputs the k smallest element, s, right? So it's a binary search tree, and we want to find the kth element in the tree. And I gave this as, it's similar to, the algorithm is basically very similar to what, we did this problem with the iterative, right? We partitioned them, and then you searched on the one or you searched on the other, right? So I thought this would be easy, right? You partition, you recurse on the one side, you recurse on the other. I thought it was going to be easy, right? But half the class failed, of course. All right, so let's kind of go through and see what happens here. I think I have it commented. All right. So here the person has added extra things up here, right? Num and v. But do I know what num and v are? I have no idea what num and v are. I don't know what the purpose of them is. All right? And then when you call on your friend, you have to meet the pre and post, the precondition. Right? So here we're calling, well, he's giving the left subtree and the right subtree, which is kind of reasonable, right? But what happened to k? And what happened to num and v? Right? You laugh, but this could have been you. It's true. It's true, it's miserable. All right, so then you ask your friend for help, right? Friend, help me, right? And what did the guy do to his friend? Nothing. He just dropped what the friend gave him into the garbage. Right? Into the garbage. All right. Now, don't save the results. Don't bug your friend. Your friend's going to hate you if you do that. All right, so now we're supposed to combine the solution we were given from our friend to get our own solution. Well, we certainly don't do that, right? Return things that are the correct type. All right, so what are we supposed to be returning? We're supposed to be returning the smallest element, right? So you're returning elements, but what are we returning down here? Well, we're returning, that one might be okay. The root of the tree, it's at least an element, right? But up here, you're returning 0. Well, now how do you know 0 is an element? How do you know it's an element of the tree? Maybe the elements are actually types of fruit, and you're wanting to return the fruit that's the smallest, and 0 is just not even a reasonable element, right? And here you say return element. Which element do you think the person's talking about? I don't know, right? And then, let's see, sub-instances need to be smaller. All right, okay, this is a hard one. All right, everybody focus. Are his sub-instances smaller?
Parts of the same tree again.
I don't know.
Okay,
He's
okay.
doing left subtree, right subtree. Right, that looks pretty good, right? Anybody see any problem with that? There's a problem here.
What about the roots?
The root? Well, he's doing something to the root. But we're talking about, is his input getting smaller?
It doesn't define what a left subtree is?
No, it's pretty, left subtree. I'm open. You give me any notation which sort of says, I'll fake it. All right, so what did I say about size? I said you have to give your friend something that's smaller according to some definition of size, right? All right, so what definition of size is he using here? Number of nodes in the tree, say, right? How do we know it's getting smaller? Well, even if there's no right subtree, the left subtree is smaller because you've gotten rid of the root, right? So, and the height's shorter, right? So, if you talk about the number of nodes in the tree, the height in the tree, this is smaller, right? What was the other requirement of size? What happens, you keep recursing, it keeps getting smaller and smaller and smaller and smaller.
Base case.
The base case, right? What do we know about the base case? If it's sufficiently small, you have to solve it yourself, right? So what's his base case? When k equals to 0, right, he's going to have a base case. But that says our size is k, right? When k is sufficiently small. Now, I don't care what your size is, but you have to be consistent. You have to have one definition of size, and according to that definition of size, the input has to get smaller, and when it's sufficiently small, you have a base case, right? In this case, you go left subtree, left subtree, left subtree, right? K, well, I don't know whether k is getting smaller because I don't even have k in here, right? But k doesn't feel to me like it's getting smaller, so why are you ever going to hit a base case? You know what I'm saying? Right, so it's getting smaller, size is the size of the tree, but then you get the wrong base case, right? Your base case should be empty tree, right? Right? This is, you're going to eventually get to the empty tree, and what's going to actually happen is you're going to get the empty tree, and then you're going to ask for the left of the empty tree, and it'll probably blow up on you. All right? All right, so here's a question for everybody. If I went right in here, what would the value of n be? And if I go here, the value of n will be 1. And you're checking whether n1 is k, right? Is that interesting? No, it's not very interesting, right? Right, so that's not very useful here. Right, this is that n's are global, you can't have a global variable. Right, I'm assuming that he's thinking that his friend's going to change the value of n. Right, and it doesn't. No global variables. All right, so maybe he has a now I'm trying to be kind to him, right? I was hostile for a while, and now I'm trying to be kind. What is this person thinking at all? Well, what's this num? It's probably maybe he's thinking about he's passing in and passing out in, right? If you passed in and then somehow passed it out again, maybe you can make n global, and maybe as he sees nodes. He's counting, right? Because he wants the case smallest. So if you kind of pull out both of this out, right? What is he doing? He's given a tree, and he recurses on the left, and he recurses on the right. Recurses on the left, looks at the root, recurses on the right. So he's doing a traversal as if it's a binary search tree, right? It's a binary search tree, and he's looking at those numbers in order, and as he goes through them, he's counting. So why he only sets n to be 0, here as opposed to outside the whole program. He should only have to, if he's counting them as he goes by, he should only set n to be 0 once. And then as he sees them, he has this global variable which counts them. And when the global variable gets to be k, he's seen enough of them, so he outputs the answer. Right? So that's what I assume he's doing. And sometimes, for amusement, I try to figure out what people are doing, right? But it wouldn't even matter, If I could kind of figure out what he was doing, maybe I'll add comments here. Hey, I kind of get you're trying to do this, but it doesn't change the fact that the mark I want to give is -100, right? And I'm sure I didn't give him more than 0. Everybody kind of get this? Is anybody going to give me this? No. Good.
Did someone actually write that, or did you make that out?
No, this was directly copied. And this isn't really even atypical. I get this kind of stuff all the time. All the time. Right? And so don't pass values in and out unless they're... Yeah, so here's another thing that people do that I hate. All right? So don't do this. I want to be very clear what values are leaving, right? So what you write here, to me, are the values that are coming in, right? And what you write here, outputs, tells me what values are going out. And when you output them, you write them here, right? I don't mind you putting a little bracket, if you return, this is one thing I hate about programming in general, right? If I'm outputting 2 values, I'm happy to say I, J, friend, right? Friend returns 2 values. I don't want to do this record stuff. What I don't like is when people put I and J here, and somehow I'm not really sure whether do I and J just go in, or do somehow they think they're coming out of here too. Do you guys ever do pass by value and pass by all those weird things? Do you ever have a programming language where things come out here? Because maybe the days of that is gone. There were certainly had programming languages where things went out, and I hated it. All right, so the other thing that's wrong with this program is, remember I said in recursive programs, you don't really have variables, right? Values never really change. As soon as you put this here, I often find my brain can look at it in a second. No, this is going to get a 0. Why waste my time on it? And one thing that I would see right away is I see ++ in here. I just say, that guy's thinking iteratively. He hasn't gotten the recursive paradigm yet, right? This screams to me iteration. and we're not iterating, we're recursing. Right? This looks recursive, that looks iterative. I get confused, sounds like he's confused, and that's life. Everybody kind of good with that? All right. Any questions about anything? So, the next topic that's officially in the course description is heaps and heap sort. How many people know heaps and heap sort? How many people want to do it again? And how many people want to do it again? How many people want to skip it? So we have some great slides here for it, and the last couple of terms I've been skipping it. Right? I mean, maybe we'll just sort of go over it go real quick. What's a heap? A heap is for every node, all its children are smaller. Right? So this is a heap because these are both smaller than 8, and these are all smaller than 6, and these are smaller than 5. Right? And it's also, rule is it has to be completely balanced. Right? It has to be of this shape. Right? It can't be of any other shape. And there's no sense of left or right being smaller or bigger. And so the 9 has to go at the top, right? The 8, where does the 8 can go? I guess the 1. The 1 can go anywhere down there, right? The 8 can go anywhere in the top 2. 8 can go over there. So, I don't know. Do you want to be doing this? Let's see. So, to make a heap, one thing, I guess what was on this back slides here, is we don't actually store the nodes in a tree, right? You store them in an array, right? And there's this mapping of how to get from here to here. And then, if you want to make a heap, well, you get your left friend to make a heap and your right friend to make a heap. And then, so those are heaps. And now, you worry about the top guy. And the top guy, who needs to be at the top here? It's the 9. Well, the 9 is the largest of these guys, and the largest of these guys is the 8, right? So we know the largest is one of these 3, right? So you compare those 3, and you swap. You put the 9 up to the top. But now you don't know that this is a heap, right? So you call, again, you know this is a heap, but you don't, and you know this is a heap, but this is problematic. So what do? Is we compare those 3, right? And it kind of bubbles down. And you can traverse through this, and it's all very exciting. So what's exciting about priority queue, about the heaps? Now this is something you should know, all right? This is what I want you to know about heaps. The only thing I'll ever ask you is, there's a data structure called a priority queue, all right? And everybody know what a queue is? Is people stand in line, and the first guy in line gets to go into the front. All right? So here's actually, let me tell you a little story which I think lets you demonstrate priority queues. All right? So if you've ever taken the 196 bus, right? Sometimes the line is really long, right? Really long line. And this one day, I was standing near the front of the line, because I'd been there a while. I'm standing there in the line, waiting for my turn. And this really gorgeous young woman comes up and starts talking to me. And I'm like, wow, really gorgeous young women don't come up and talk to me very often, right? So I'm kind of thrown for a loop, and I chat with her. And then the bus comes, and we both get on, and she disappears. And I realize what happened. That was a priority queue, right? She butt in line. All right, so what is a priority queue? It's is that the people of most priority got to get on the bus first, right? So a heap, what you do is you have all these objects, and their priority is the value. You know, you put them in a heap according to their priority, right? And then there are various things that you can do which are exciting. One is you can grab the thing of highest priority from the heap. Where is it? It's at the root. Now, if you take it out, now what's the problem? Is you don't have the loop invariant anymore, right? It's no longer a heap. So how do you make it back into a heap?
You take the bottom element, put it at the top.
Yeah, we want to keep the shape, right? You got to keep the shape. So you take the bottom guy, the last guy in the array, and you put it at the front, which is the top guy. Now the left is a heap and the right is a heap, but you're worried about the root. So the root kind of bubbles down. You know, you keep compared to the 3, the root bubbles down. So that's how you pop something from the heap. It takes, how much time does that take? Log n, because it's the depth of the tree, right? Now, the other thing you can do is you can insert somebody, right? How do you insert it? You put it at the bottom, and it bubbles up, right? That also takes log n time. The other thing you can do is you can leap, if you have pointers into these guys, right? You can follow a pointer, you can leap into somebody in the line, and you can change their priority, right? And when you change their priority, what happens to them? They bubble up or bubble down, right? Does that kind of make sense? And so the joy of this is every operation takes log n time, right? In contrast, what's the obvious thing to do for a priority queue? Well, if you sort everybody by their priority, well, then it's hard to insert things. It's hard to, it's easy to grab someone from the top, but then you have to shift everybody, right? That's a pain. The other option is you don't sort them, and then you have to search for the best guy, right? Those kind of take order n time. Well, heaps are really good for taking order log n time operations, all right? So that's what I want you to know about heaps, is that they're good for priority queues, which take log n time per operation. Here, I guess. Yeah, we're still doing binaries. We're still doing heaps. See, I got a lot of slides. Oh, here we go. Let's do something else now. All right, this is fun. All right, heaps were kind of fun, but I gave you everything that was kind of interesting. All right? Now, one thing that trees are good for is for storing expressions like this. Right? Because you can see that this is 3 times 4 plus 7. It gives you the order of operations, right? Without the brackets and stuff. In fact, if you were a compiler or or you were trying to read some document in English, the first thing you would do is you would parse it and you would build some sort of parse tree like this, an expression tree. Right? And we're going to talk about how to do that later. But everybody kind of get this tree here? Now, how would you evaluate this tree?
You start from the bottom first?
No, absolutely not.
Do that, do that.
In order.
Start from the top and then recurse on the left and
We're doing recursion here, guys. What do you ask your left friend? Your left friend evaluates this and gives you a 12. The right friend evaluates this and gives you a 7. Now what do? You say, hey, I'm a plus, so I add them, and I return the answer up. Right, everybody get that? That's the entire algorithm. Base case, What's the base case?
When you have only one on the left and one on the right.
You mean like this? What about this? What about the empty tree?
0.
Yeah, well, empty tree is kind of funny, right? Because this isn't really an operation, right? One reason we like the empty tree is because in case you had a left and didn't have a right, but here, you know, we're going to have the base case just be a number. All right, so here's our code. This is all the code you need to be evaluating these things. All right, so what are we given? We're given a tree, f, because it's a function, and it's going to be a tree with times and plus and divide and all the various operations that you want. And the leaves are going to either be numbers or they're going to be variables. And the variables will be x, y, and z. And what we want to do, and part of our input is the current value of x, y, and z. And we want to substitute those values, current values of x, y, and z into the variables, and then we want to evaluate the tree. Everybody got that? What the problem is? So, if f is a real value, like 5, then what's the answer? The answer is 5, right? If f is simply the variable x, then the answer is the value of x. If f is y, it's y, f is z, it's z, right? Otherwise, if f, the root of f is a plus, right, then what's the answer? I evaluate the left on the same values of x and y and z. I evaluate the right, I add the two together, and I return the answer. Right? Can't be easier than that. If it's a subtraction, I do the same, but I subtract. If it's a times, I do a times. If it's a divide, I do a divide. If it's an exponentiation, I exponentialize. Exponentialize? Is that a word? You know what I'm saying? Everybody kind of get this? I mean, this is kind of where recursion is really, it's really the way to go. Right? 3 minutes left. All right. All right, so now, in 3 minutes, everybody remember calculus? Can everybody take a derivative? Can you write a program to take a derivative? Can you write a program to take a derivative in 3 minutes?
No way.
All right. So here, the input is some function like this, and the output will be another tree, which is the derivative. All right? Can you believe that we can do it in 3 minutes? No. Okay. That's the derivative. Right? So that's the input, that's the derivative. Everybody got that? You see how that's the derivative? No. Yeah, sure. All right, so here's the code. Here's the code, all right? I'm given f, and I'm given what variable we're differentiating with respect to, right? And if f is the variable x, what's the derivative? 1, right? And I construct a tree that's just 1. It's not 1's the answer. It's a tree that's 1 is the answer, right? If f is a constant, 5, or the variable z, then the answer is 0, right? Otherwise, I take the derivative of the, I copy the left subtree. I don't want to destroy the tree I have when I create the derivative, right? I want a brand new derivative tree, right? So I copy the left subtree. I copy the right subtree. I take the derivative of the left subtree. I take the derivative of the right subtree recursively. Right? Everybody got that so far? And then, if my function is a plus, then what's my answer? Right? It's the derivative of the left plus the derivative of the right. Right? If it's a times, then you have to build this crazier structure, right? It's the derivative. It's g prime times h plus g times h prime. Right? And if it's a divide, then it gets stranger. And that's why our example had so many divides and it got so ugly. Right? Everybody kind of buy that? And that's the entire program. So we did it in 3 minutes. Everybody kind of follow it?
back a couple slides.
Oh, we're supposed to be awed and impressed. How far back are we
There we
going?
go. Oh, one more forward. There we go. You're copying the left subtree to G.
Uh-huh.
And you're doing the derivative of
The left subtree.
So why did we copy it?
Well, because if we just used it, right? We have this data structure H, and we're building a new tree. Well, we don't want pointers here pointing into data structures there, right? We want our own clean copy here.
So that's the one we used in the second last line. That's the copy?
It's the, yeah. So, oh, you mean where we're taking the derivative?
Yeah, like that.
It doesn't matter, because these are going to give you a new one,
Okay.
right? So copy will give you a new, this will give you a new, derivative will give you a new, this will give you a new. Right, so now we have these 4 new things from which, and we build them. We use them to build our tree. Does that make sense? So, we probably don't have any time left, but what we're going to do, well, we maybe got 1 second left here. Suppose we want to simplify the tree, right? If that's the input, we want to simplify it. We want to simplify it down to something really easy, right? And how do you simplify it? Well, if f is just a single real value or variable, then you just copy it. And otherwise, you recursively simplify the left and the right. And then you do the obvious rules, right? If it's 1 times h, then you just replace it with h. 0 plus h is h. 0 divided by h is 0. Right? You just use the obvious local simplification rules, right? And it turns this into that. Right? Everybody kind of buy that? And that's it. So have a great week. And on Monday we'll keep doing recursion. There's probably another class, 1 more class in recursion, and then we'll start doing depth first search, breadth first search, and then we'll do more graph algorithms.